Teams ship features that do not help users because they celebrated a tiny p-value once and never noticed they increased a different kind of mistake. The gap is thinking a significance threshold protects you from all error, or worse, that it tells you the chance your conclusion is true. What actually happens is that any test rule draws a line through overlapping distributions, so making false alarms rarer automatically makes misdetections more common. Picture yourself in a sprint review, a dashboard flashes a p-value less than 5%, everyone nods, and no one asks which way the test just failed more often. A hypothesis test is a decision rule disguised as ritual. You set up a default story, the null, and an alternative story, the effect you care about. You compute a statistic from the sample and compare it to a threshold. Cross the line, and you reject the default. Do not cross it, and you keep it. That threshold is a knob, not a fact of nature. Type 1 error is rejecting a true default. It is a false alarm saying you found an effect that is not really there. The long-run rate of this mistake is whatever significance level you chose before you looked. That is not a label of truth. It is the fraction of worlds with no effect where your procedure would still shout, yes. Type 2 error is failing to reject a false default. It is a miss, looking at a real effect and shrugging because your data did not push the statistic past a line. Its rate depends on the true effect size, your sample size, the noise in the data, and the position of the threshold. The complement of that rate is power, the chance you would detect the effect if it were there. Here's a concrete picture. Think of a medical screening tool that outputs a risk score. You set a cutoff on that score, set it too low, and you send healthy people for needless follow-ups. Set it too high, and you send sick people home undiagnosed. The tool has not changed. Your cutoff decides which mistake you prefer to see more of. The common beginner mistake is to treat the significance level as the probability the default story is true after seeing your data. That is backward. The significance level is the chance your rule would have signaled an effect if the world actually had none, averaged over many imaginary repetitions. Mixing up those directions leads to overconfident claims and brittle models. The cost of that mistake shows up two ways. First, you accept spurious wins, reroute resources, and then cannot reproduce the result because you misread a false alarm as a discovered truth. Second, you quietly run underpowered tests that almost never catch effects of plausible size, so you throw away useful changes because the statistic did not jump high enough once. You end up oscillating between chasing ghosts and missing signals. There's a clean correction. Decide before the data what effect size matters for your decision, not what effect you hope to brag about. Use that to plan a sample that reaches a target power, like 80%, at the threshold you can justify. Now your test is tuned to what you care about, not to an arbitrary ritual. Here's why that works. The two error rates trade off because the sampling distributions overlap. Moving the threshold to reduce false alarms pushes the bar higher, so real effects must be stronger or better measured to get over it. Collecting more data narrows the spread of the statistic under both stories, which reduces both kinds of mistakes at the same threshold. If you cannot collect more data, you must choose which failure you would rather tolerate more often and say that choice out loud. Another trap is multiple looks and many tests. If your significance is 5%, running dozens of comparisons or peeking at the data every hour mechanically inflates your chance of at least one false alarm. Nothing mystical is happening. You are rolling the same die again and again until it comes up special. The fix is to adjust the threshold when you run many tests or to reserve a held-out evaluation and look only once. Peaking early and often has a second effect that people miss. It shortens the average sample at which you make a decision, which usually raises the miss rate because weak true effects do not have time to accumulate signal. Sequential designs can be done correctly, but they require explicit rules for when you stop, and they must adjust the error accounting across the whole path. If you are not ready to do that math, set a fixed sample and hold yourself to it. Stop treating the two error types as moral categories. They are costs. In medicine, a miss can be worse than a false alarm. In fraud detection, false alarms might swamp your investigators. In product experiments, a false alarm burns engineering cycles while a miss delays learning. The right threshold is the one that minimizes expected loss under your stakes, not the one that stamps the prettiest label on your slide. A crisp mental model helps. Imagine 4 boxes formed by reality on one side and your decision on the other. True with accept means you were right to do nothing. False with reject means you were right to act. True with reject is a false alarm, a type 1 error. False with accept is a miss, a type 2 error. Every test outcome lands in one of those boxes, and your design changes the frequency with which cases fall into each. Power and significance are levers, but they are not the only ones. The minimal effect you care about is a lever. The variance of your measurement is a lever. You can reduce noise by improving your measurement process, tightening protocols, or blocking on relevant covariates. You can increase signal by making the treatment stronger. All of those change the overlap that creates both error types. Look closely at p-values when you read a report, but do not stop there. Ask what default story was tested, what alternative was meaningful, what minimal effect was promised, and what power was achieved. Look for confidence intervals that show how precisely the effect is estimated, rather than just whether a threshold was crossed. If you see a small p-value alongside a wide interval in a tiny sample, expect volatility and plan a replication before acting. In online experimentation, the same logic holds. A low false alarm rate without power planning makes product roadmaps nervous and indecisive because every test drags on and misses moderate wins. A lax threshold without holdouts creates a parade of illusions that break when rolled out broadly. The discipline is to pre-commit. Define the metric, the minimal effect, the sample, the analysis plan, and the carry decision for each possible outcome, including what you do if the test lands in the gray area. Intuition often breaks because people think the truth is a single cliff and a test is a flashlight that either reveals it or not. The correct model is overlap and trade-off. 2 stochastic worlds, 2 bell-shaped sampling pictures, and a movable cut. Changing the cut trades, 1 error for the other, unless you also change the width of the bells with more data or better measurement. That is the geometry of testing, and it does not care how you feel about a threshold. The single shift this lesson asks for is simple. Stop asking, did we win? And start asking, which mistake did we make cheaper, given our stakes, and did we invest enough data to keep the other one acceptably rare? A p-value is not a verdict. It is evidence run through a rule you chose with predictable failure modes you can audit in advance. Good testing is explicit about those modes, not surprised by them afterward. Next, we will see why averages settle down, why sampling pictures look bell-shaped, and how that makes power and error rates computable in practice when we study the central limit theorem, the most powerful idea in all of statistics.